Good morning, everyone. It's my great pleasure to be here to attend this wonderful international conference. My name is Chuan Wen, and I'm an assistant professor at the University of Exeter in the United Kingdom. For today's presentation, I'd like to talk about a new concept to remove the carbon dioxide from natural gas using the phase change in subsonic flows, which can contribute to the carbon capture and storage. As far as we know, the global warming and climate change is one of the main concerns in our current society, not only for our academic colleagues, but also for the general public. And the carbon capture and storage is recognized as one of the promising technologies to combat the climate change. And currently, there are a few conventional technologies to remove the CO2 from natural gas industry, including the refrigeration, absorption, adsorption, and the membrane technology. This technology shows good performance for the onshore applications, like the power plant, but it is very hard to directly extend these technologies to the offshore natural gas industry because of the limited space of the offshore platform and the safety issues for the offshore gas industry. And for this purpose, we'd like to propose a new concept to remove the CO2 from natural gas using the phase change in subsonic flows. And this concept integrates the ideas from the aerospace engineering and chemical engineering. Firstly, we use a lava nozzle to generate the phase change, which can achieve the massive droplets in subsonic flows. And secondly, we use the static vanes to generate the cyclone separation, which is widely used in chemical engineering. And for this new concept, the most important step is to evaluate the potential of the generation of the nucleation process and droplet growth process. And here's a short video to show the working principles for this new concept. We can see that for this new device, we have some good advantages. For example, small size and lightweight, and also the tubular device doesn't contain any rotating equipment. Also, it doesn't need any chemicals to prevent the hydrate, and so it has no emissions to the environment. And also, it is very suitable for the application in offshore gas industry because of it enables unmanned operation for personal safety. And in this study, we try to evaluate the potential of this new concept to remove the CO2 from natural gas. And in the numerical simulation, we try to describe the gas-liquid mixture, use the conservations of mass, momentum, energy, and also we need another two scalar equations to describe the phase change process. The y equation is to describe the liquid fraction, while the n equation is used to describe the liquid numbers during the phase change. And here we use the J to describe the nucleation rate in the nucleation process. And the dRdt is used to describe the droplet growth rate. And also we need to couple the heat and mass transfer during the phase change in supersonic flows, and therefore we will employ the source terms to the mass, momentum, and energy equations to describe the latent heat during the generation of the massive droplets in this concept. And next, we tried to validate our developed safety model using two cases. The first one is the CO2 in high pressure conditions. And here we show the result between the experimental and numerical results. We can see that the calculated pressures agree well with the experimental data. But the problem is we have no data for the validation of the droplet size or liquid fraction, which are the main parameters for the phase change behavior in these supersonic flows. So we use the second case, which is employed the water vapor as the working fluid, and the pressure is about 90 bar at the inlet of the supersonic nozzle. And here we show the comparing between the experimental and numerical result of the static pressure and droplet size. We can see that both the static pressure and the droplet size shows a good agreement between them. So based on these two validations for the CO2 and water vapor, we can say that the developed safety model is accurate to describe the phase change in supersonic flows. And here we have some animations to show the parameters of the phase change in supersonic flows, and including the nucleation rate, the droplet diameters, droplet numbers, and the liquid fraction. We can see that both the nucleation rate and the droplet numbers is very high for this phase change in supersonic flows, and the diameter of the droplet is about 35 nanometers, and the liquid fraction can reach about 6% of the total mass. In the next few slides, I'd like to show you some results from our numerical studies. Firstly, we'd like to compare the dry gas model and the wet steam model in the prediction of CO2 condensation in supersonic flows. In the left figure, we can see that the dry gas model predicts higher Mach number and lower pressure than the wet steam model. And at the outlet of the lava nozzle, the difference of the Mach number is about 22%. And in the right figure, we can see that the dry gas model predicts a lower static temperature than the wet steam model by 25 Kelvin. This means that the dry gas model overpredicts the gas expansion characteristics than the wet steam model. And also we can see that the wet steam model predicts the condensation shock. This is because of the latent heat during the phase change in supersonic flows. And also we can see that the nucleation rate is very high in this case, like about 10 power 20 per cubic meters per second. And in this specific geometry of the supersonic nozzle, the liquid fraction can reach about 2.5% of the total mass. Secondly, we try to evaluate the effect of thermodynamics model in the prediction of CO2 condensation in supersonic flows. We employed the ideal gas model and the real gas model to describe the thermodynamics properties in the phase change in supersonic flows. And the most important, we can see that this IDX model predicts lower mass flow rate compared to the real gas model. And the relative error can reach about 25% at the inlet pressure of 50 bar. And also the two models give different flow structures in supersonic nozzles. And in this figure, we can see that the IDX model predict higher Mach number in the divergent part of the supersonic nozzle. And the relative error can reach about 10% at the outlet of the nozzle. And the right figure shows that the IDX model will predict a lower temperature compared to the real gas model. And the most important, we can see that the IDX model will predict a higher jump of the condensation shock. This means that IDX model overpredicts the gas expansion process, as well as the heat and mass transfer process during the CO2 condensation in supersonic flows. And also we can see that these two models predict different onset of the nucleation process. And also the most important, we can see that the real gas model will predict like 2 times of the liquid fraction than the IDX model. This means that for the prediction of the phase change, the IDX model will underpredict the generation of the liquid phase during the CO2 condensation in supersonic flows. Thirdly, we'd like to evaluate and optimize the effect of nozzle converging profiles on the prediction of CO2 condensation in supersonic flows. Here we employed 3 profiles to design the supersonic nozzle, including the straight line, circular arc, and cubic polynomial. From the distribution of the Mach number, we can see that the straight line will generate very strong shock waves in the divergent part of the supersonic nozzle. On the contrary, the circular arc and cubic polynomial case will weaken this behavior. Also, we can see that these 3 profiles will affect the phase change process. We can see that the straight line will give a later onset of the nucleation process. And although these 3 profiles generate almost the same distribution of liquid fraction, we can still observe the shock waves generated by the straight line. And for the condensation loss, we can see that the straight line will result the highest condensation loss compared to the other 2 cases. Now we can conclude our numerical studies for the CO2 condensation in supersonic flows. Firstly, we proposed a new concept to remove the CO2 from offshore natural gas, which can contribute to the carbon capture and storage. Secondly, we developed and validated the CFD modeling for the prediction of CO2 condensation in supersonic flows. Thirdly, We evaluated the wet steel model and real gas model for the prediction of CO2 condensation in supersonic flows. And also, we tried to evaluate and optimize the effect of nozzle converging profiles in the prediction of CO2 condensation in supersonic flows. Finally, we'd like to thank the financial support from the Mercury Fellowships. That's all for my presentation. Thank you very much.